Hi, everyone. Welcome to the Qlik Talend virtual meetup. I'm Evan Leung from Pingahla, and I'll be moderating today. Again, just a quick heads up, we are recording this session. So if you have any questions, please save it for the end where we'll have a Q&A. And also just be sure to mute yourselves or keep yourselves muted into the Q&A as well. So just a quick agenda and our plan today. So we'll provide some quick info and instructions on the giveaway rules we have today. I'll give an intro just of our speakers. We'll go through a short recap of Qlik's AI reality tour in New York City. And then we'll begin deep diving into the presentation itself, just starting with an overview of the open lake house and Apache Iceberg, followed by a deeper dive and demo from Jason and Qlik themselves. Then we'll finally do a Q&A and wrap up the presentation. So for the giveaway today, as you may have seen already, there are two giveaways. So there will be a $10 DoorDash or Uber Eats e-gift card. The instructions I'll go over in the next slide. And then there's also going to be a set of Beats headphones, actually, where we'll draw a winner and announce it roughly around next week. So in terms of the instructions and how you can kind of apply for this giveaway, so kind of two quick steps. So first, you'll need to register on Pingahla's form and include your Zoom display name that you have here. That's just kind of how we're going to verify attendance. And then the second link will actually be for completing Qlik's short data maturity assessment. So I'll provide both of these links in the chat as well. And then what you'll also need is a secret phrase that we'll share at the very end. It won't appear in the recording, so be sure to kind of stick around, and then it'll be at the end when we wrap it up. And then just a couple of notes. You will need to use your work email, so no personal Gmails or anything like that. And Qlik will also cross-check your submission, with your Zoom name, as I mentioned, before providing the gift card. Right. So kind of just a quick intro on our speakers today. Again, my name is Evan Leung, so I'm just the moderator for today. And I'm from Pingahla, and I lead our professional services team as well as delivery for the Americas side. And with me, I have our consultant, Nicolas Diaz, and he'll help provide the overview of Apache Iceberg and Lakehouse. And then we have Jason Hall, Principal Solutions Architect from Qlik, that will deep dive into Qlik's Open Lakehouse, as well as walk through a demo. And then a big shout out again to Qlik, our partners here today. So just a quick recap on kind of Qlik's AI reality tour in New York City. Many of you may have already seen, but at Qlik's AI reality tour in New York City this year, there was a lot of fantastic customer stories, and also sessions with leaders like Mike Capone. And if you did miss it, you can definitely go and check out the online recap. And also a quick heads up that for Qlik Connect 2026, that will be in Orlando, Florida. So we hope to see you all there soon. And with that, I'll pass it over to Nicolas, who will begin with our overview.
All right, thank you, Evan. Hello, everyone. Hope everyone is having a good day today. Hopefully you saw anything interesting for the AI reality tour. If not, here we have a little bit of a sneak peek of what it can be viewed in that conference. And before we start, let's see how we got here. Let's take a quick history lesson to understand how we got all the way up here. So, like in the late 80s, we had the data warehouses. These are large databases that consolidated structured data from smaller databases through traditional ETL pipelines, right? Everything was consistent, schema-based, relatively clean. And for the sake of the argument, let's say it was clean and organized. Let's say that unquote unquote, because sometimes it was not. But around the 2010s, the world changed. We had the rise of the internet, the rise of smartphones, and the rise for the need for real-time data access. And that meant that massive volumes of data started to saturate those ETL pipelines. So integrating the data was becoming more tedious, more slow, and of course, more expensive. But then someone had a brilliant idea, an amazing idea. He said that someone said, what if we stop transforming the data before we load it and instead transform it only when we needed it? Well, with that, everything changed. So we shoved the schema to the side and gave birth to Hadoop, or what we now call data lakes. So these data lakes are massive cloud storage systems and solutions where we could dump data into S3 buckets and transform them later when we are retrieving them, right? It was perfect, it was nice, it was great until a certain point, because then we realized something critical, like a big problem. And that was that data lakes became swamps. And that happened because we were dumping a bunch of different files, formats, and raw data that that basically became poor performance for business intelligence and data analytics. And of course, we were lacking in data reliability and security. So in other words, we realized that schemas still matter. So that's when around the late 2010s, early 2020s, a new challenger comes in. And that's it, Apache Iceberg. So Apache Iceberg, I think a lot of you already know. If not, is basically an open table format for data lakes. It's gonna track metadata about data files in a tree-like structure, and it's allowing the user to manage tables inside data lakes with database-like features, such as schema evolution, ACID transactions, time travel queries, and hiding partitioning. In short, Iceberg is bringing a structure and governance to the chaos that it was the data lakes. Thanks to these kind of technologies, the concept of data lakehouse was born. So what exactly is a data lakehouse? We can show you how the architecture is done. So a modern lakehouse architecture usually includes 6 layers. An ingestion layer that is basically you're bringing the data from different sources. So both, it can be streaming or it can be batch. We have our storage layer that, like it says, is storing all our data. It can be in an unstructured manner or in an unstructured manner. We have our physical data layer. Basically, you choose how you want to physically store your data. It can be in packet format or ORC or APCO. We have the metadata layer. That's where Iceberg is located to manage all the raw files, those schemas, versions, snapshots, all of that can be done there. Of course, an important layer is the governance layer. Here we can maintain the data quality and security and the compliance, following all the rules. And finally, the query engines, where you can decide whichever engine you want. It can be Spark, it can be Snowflake, AWS, Presto, Dremio, whatever, and you can analyze and process your data directly from the lakehouse. There you go. So for years, we have dealt with data silos, especially in cloud data warehouses, where storage and compute were tightly coupled. This was great for analytics, but it was a headache when we're dealing with massive amounts of data and real-time needs. Now, with Data Lakehouse, we have the best of both worlds. We have the scalability of data lakes, but we also have the performance, reliability, consistency of data warehouses. And because we use open table formats like Iceberg, multiple compute engines can interoperate between each other without needing to pre-transform it first, bringing true flexibility and interoperability. But of course, this also enables seamless querying, real-time analysis, machine learning pipelines, and powerful business, all from the same data source. But of course, not everything is perfect. The real world is not all sunshine and rainbows. Data lakes, while they are powerful, still face some serious challenges, especially when we're dealing with large amounts of data, especially when we're doing it in production scale workloads, right? So, for instance, large-scale ingestion into Iceberg tables can be complex and resource-intensive. Real-time transformations of raw data add another layer of complexity and latency and architectural complexity. And on top of that, building and maintaining data pipelines often means dealing with complex and error-to-prone code. Pretty common, really. And the worst part is that it doesn't stop there, really. It the part of the optimization when we're trying to optimize Iceberg tables like compaction and partitioning tuning, we're still relying a lot in manual configurations. And that in a large scale can be a nightmare. And finally, ensuring data quality and trust is still a constant struggle. Like we know that. We always have to put that data, always have to clean it, we have to deduplicate it, we have to validate it. And when we have a lot of it, it can get out of our hands. In short, well, Iceberg and Lakehouse solve many of the old data problems we have with the other solutions. It doesn't erase all of the complexity. These challenges make it even more important to crack these kind of challenges to remove them because right now the adoption of Lakehouse are becoming a standard in the industry and is growing rapidly. Here is where our savior comes in. Qlik Open Lakehouse. This is the newest addition from Qlik that they recently acquired Absolver, a powerful platform that is handling the data lakes and integrating it into Qlik Talend Cloud. This integration has boosted Qlik's data pipeline capabilities, turning QTC into a more robust end-to-end platform for managing data ingestion to analysis. From ingestion to analysis. In simple terms, Qlik Open Lakehouse is an app within QTC designed to ingest, process, manage, and optimize Iceberg-based lakehouses. So, and like I said before, it is pretty important we have this tool is coming to the table. Like the industry momentum is going all in. Right now, it is estimated that by the next 3 years, over 50% of all analytic workloads will rely on data lakehouse. Like I said before, this isn't just hype. Like it's really coming together. Every major platform is investing heavily in open table formats. That includes AWS, Snowflake, Google Cloud, Databricks, and more. So right now, I'm passing to Jason, and he's going to explain you detail by detail how this tool is working and how it can help you in your analytics pipelines.
Awesome. So yeah, thank Nicolas. As introduced, my name is Jason Hall. I've been at Qlik for about 9 months now. I actually came to Qlik via this Absolver acquisition that was referenced here. And just for a little bit of background for those that may be unfamiliar, Absolver has been in the market for around 10 years, so about a decade of experience. And Absolver's primary value proposition was around helping customers make data lakes and lake houses well performant and efficient at scale. Absolver started working with Hive-based data lakes back in the mid 2010s, and over the last several years has kind of shifted in its approach to helping organizations with Iceberg and specifically solving many of the challenges that Iceberg introduces at scale. And when I say scale, I'm referring to both volumes of data, multi-terabyte, petabyte scale, but also frequency and velocity of data, right? Kind of adapting and managing Iceberg to handle real-time and continuous workloads. So back in January, Absolver was acquired by Qlik, specifically with the goal of integrating the Absolver technology into Qlik Talend Cloud so that Qlik can provide a managed open lakehouse experience for working with high-scale real-time data. And so that's what we'll be presenting today, both from a what's available perspective, why it's important, and then we'll give you a quick demo of how the Open Lakehouse works within Qlik Talend Cloud. So there's really three primary objectives of the Qlik Open Lakehouse. And we've got a general architecture diagram here on screen, and I'll call out some specific elements of the architecture that I think are worth mentioning. But first and foremost, the Qlik Open Lakehouse is a feature of Qlik Talend Cloud, right? So this is not a separate product. It's not anything net new. It's customers of the Qlik Talend Cloud can take advantage of the Qlik Open Lakehouse to drive their Iceberg initiatives. The Qlik Open Lakehouse will ingest data from any of the Qlik Talend Cloud CDC type sources. Right? So when you look over on the left, we can work with data coming from databases like Oracle and SQL Server and PostgreSQL. We can work with data coming from SaaS applications like Salesforce.com. And later this year, we're looking to introduce support for streaming sources, for example, data coming from platforms like Kinesis and Kafka. Really, again, just kind of continuing our integration of real-time streaming type workloads. And that first capability that we're offering is specifically high throughput ingestion, real-time ingestion into Iceberg, right? So you've got this source data, you want to bring it into Iceberg, we can help with that. The second capability that we're offering is what we refer to as our Adaptive Iceberg Optimizer. We'll go into a bit more detail here in a few slides about what that entails, but the goal of the optimizer is to make sure that your Iceberg-based data lakes are operating at peak efficiency. And that means both from a context of how much storage is being consumed, right? Maintaining your data on a minimal amount of storage, but also that it's delivering good query performance to whatever engine might be consuming that data. Many organizations struggle with data lake projects because they cannot meet their query performance SLAs, and they oftentimes revert back to maybe warehouse or database-based projects, not because their lakehouse technologies can't deliver good query performance. It just is harder to deliver good query performance. And so our adaptive optimizer kind of offloads much of that optimization work. And then the third primary capability of the Open Lakehouse we're referring to as data warehouse mirroring. This is making your Iceberg data accessible and consumable by the data warehouses that you leverage. And that concept of a mirror is important. It's not a copy of the data sent to the data warehouse. It's a reflection of your Iceberg data in your data warehouse so that you can query it and consume it via the rest of your data architecture. We'll talk about each of these capabilities in more detail as we progress through the presentation. But again, as a summary, Open Lakehouse, it's a capability built into Qlik Talend Cloud that offers high throughput ingestion into Iceberg, continuous and adaptive optimization, and finally mirroring to the data warehouse that you consume data in. One last thing I'll mention on this slide, the openness of this lakehouse is a primary objective of the platform, right? It's in the name of the function, but I wanted to highlight the fact that everything that Qlik Talend Cloud is doing and creating for you is open across the industry. We're not locking this format in across necessarily even Qlik, let alone a particular data platform. We're storing our data in the open Iceberg table format. We leverage existing Iceberg catalogs such as AWS Glue, Polaris, Snowflake's Open Catalog. And you'll see over on the right, you're able to query data from a wide variety of query engines. So whether you use Snowflake or AWS Athena or open source Presto or Trino, what Qlik is doing within the Open Lakehouse, one of our primary objectives is that the data is not locked into a particular format and is open and accessible across the wide industry of ecosystem, the wide industry that's again rapidly adopting Iceberg as a standard table format. Okay. So let's go into each of the three features here. So the first I wanted to touch on is real-time ingestion, right? Ingesting data into Iceberg. And when we talk near real time, we're referring to those use cases that require near real-time freshness of data, right? Near real time being, anywhere in the few seconds to a few minutes range of data freshness. So let's assume you've got transactional data being written maybe to an Oracle database. If you want to drive analytics off of data within a few minutes of that data being created on the source. And real-time ingestion is a challenge even at low scale, right? Just the frequency of ingestion becomes a challenge. But then applying real-time ingestion at massive scale adds a whole other range of challenges to how data needs to move through a system. So this is one of the benefits that Open Lakehouse provides, and is something that the Upsolver engine has provided for many, many years. We have customers processing data in the millions of events per second range, in the multiple terabytes of data an hour range. And this supports both batch and streaming ingestions into Iceberg at, again, very high scale. And something I do like to mention, it's not necessarily called out on this slide, but I often like to use the term simplicity at scale, right? Whether you're working with a few changes per second or a few million changes per second, the user experience within Qlik Talend Cloud is the same. The product was really designed to where, and I'll show you this in a demo, with a few screens and a wizard and a few simple configurations, you can set up a very high scale streaming pipeline into Iceberg. And know that that will be able to keep up with very high volumes of data. Now, why is high scale a challenge within Iceberg? All right, so we'll kind of backtrack now into the Iceberg format itself and kind of why does high scale ingestion a challenge that many customers need help with? So if you look at the Iceberg architecture over on the left, one challenge that becomes difficult to work with within real-time ingestion into Iceberg is that every write to Iceberg is going to generate a new set of files that needed to be added to a table, right? Let's just think of a single Iceberg table for now, right? Every time we write to Iceberg, we add data files to an Iceberg table, right? Let's think about a real-time ingestion where we're writing data once per minute, right? That means that at minimum, once per minute, we're going to get a new data file added to our Iceberg table that makes up the full data volume within that table. Now, there's a very common problem. It's actually existed in data lakes for years, decades even, it's often referred to as the small file problem. And anytime you're doing real-time ingestion into Iceberg, you naturally end up with lots of small files, right? Hundreds of thousands, maybe even millions of small files as you continuously write data into that table. Well, anytime you run a query against an Iceberg table, that query, in order to return its data, has to open every file that contains data that needs to be returned. And actually, technically, when it's done reading data, then has to close the file. And opening and closing a single file is a fairly trivial amount of work. Opening and closing hundreds of thousands to millions of files is a significant amount of overhead on query performance, even before you consider reading and processing the data itself. So again, with data lake tables, when you have lots of small files, there's just fundamentally a lot of overhead placed on the performance of queries, just due to the fact that you have to open and close all of these small files. So that's very much a consideration that needs to be considered within Iceberg tables. Another consideration with real-time ingestion into Iceberg is that every time you write data into Iceberg, it generates a snapshot. And these snapshots are maintained in a set of metadata files that make Iceberg deliver its intended functionality, right? Some of the features that Nicolas mentioned are ACID-compliant transactions and the ability to do time travel and the ability to evolve schemas. Those capabilities exist because of the snapshot-based architecture. Right, so you write data into Iceberg, it creates a new snapshot. That snapshot references the files that make up the table. And over time, you generate lots of snapshots, right? Again, every time you write into Iceberg, you get a new snapshot. Each snapshot is going to take up space within the Iceberg metadata files. Having lots of snapshots present in a set of metadata files can also add query time and overhead to query performance. If you've got 10,000 snapshots within a metadata file, before your query even starts running, it has to scan these large metadata files, determine what snapshot you want to read from, and then find all the files that are referenced by that snapshot in order to process your data. Right? So these large metadata files over time can be very expensive to scan. Another characteristic of real-time ingestion into Iceberg is the idea, and Iceberg has a, I don't know that I want to call it a feature, but it's a design of Iceberg that's referred to as optimistic concurrency. And that means in order to speed up ingestion performance, Iceberg uses an optimistic concurrency model. What that means is that data is first written to disk, right? So when you write data to an Iceberg table, it creates all of the data files needed to store that data. And then after the data files are created, it tries to commit that data to the table, right? It tries to create a snapshot, create all the metadata that points to those new files, and then assuming that goes successfully, your files now are an active part of the table. But for a variety of reasons, there could be times where those commits fail, right? We write the data to disk, but we're not able to commit that data to the table. Those files don't get cleaned up, right? They're actually referred to in the Iceberg world as orphaned files. And this is just the nature of Iceberg doing what it's intended to do. There's no way to prevent them. They could orphan files can create many times, and oftentimes for very valid reasons that those files are created. But we've seen issues at scale with real-time ingestion where you end up with lots of orphan files, which can dramatically increase the amount of storage that your table takes on disk. You might have 100 gigs of data that's consuming 500 gigs on disk because you have 400 gigs of orphan files that need to be cleaned up and managed. So all of these characteristics are symptoms of doing low latency, high scale ingestion into Iceberg. Pivot now to the second capability that I mentioned within the Qlik Open Lakehouse, and that's the adaptive optimizer, which takes care of optimizing Iceberg based on those three characteristics of low-scale ingestion. Right? This is often referred to as the secret sauce that makes Iceberg function at scale. Right? When you're doing high-scale real-time ingestion into Iceberg, it simply won't function and deliver its value unless you have an answer for continuous optimization, and that's what the Open Lakehouse provides. There's a couple capabilities of the adaptive optimizer that we're going to talk through. Now, a key takeaway of this adaptive optimizer is I'm going to explain to you what's happening under the covers here, but from an end user perspective, this is all fully automated. It happens behind the scenes. It happens continuously. There's no manual buttons you have to push. There's no tasks you have to schedule. Whenever you ingest data into Iceberg with a Qlik Open Lakehouse, the adaptive optimizer just happens, right? It just runs in the background and ensures your Iceberg tables are running at peak efficiency. Now, what are we doing to ensure that? The first is cost-based compactions. Now, compactions fundamentally within data lakes, a compaction is effectively the process of taking lots of small files and rewriting them into fewer, larger files, right? For peak query performance, a table would be much better served by, for example, having 100 large files versus 100,000 small files, right? Because the overhead incurred on query performance by opening and closing 100 files is much less than opening and closing 100,000 files. So compaction is absolutely something that needs to be done on data lake tables in order for them to run efficiently. Now, in a small scale workload or a batch-oriented workload where you're only updating data, let's say once a day, compaction is fairly straightforward, right? It's a single command that you can run in Spark. It's a single operation that you can schedule using a variety of query engines, and it will simply just compact all of the data, right? But at scale and with real-time workloads, it's impractical and inefficient to run compactions all of the time, right? So our cost-based compactions it's an algorithmic-based approach that collects metadata about your Iceberg table. It then feeds that metadata into a prioritization algorithm. And then we basically prioritize which compaction should we do continuously based on the need to compact, the benefit of the compaction, and the available resources in order to perform the compaction. Again, this is nothing you have to even think about or consider. Just know that it's happening in the background. We're continuously compacting data. We're prioritizing the most beneficial compactions. And the end result is an iceberg table with a healthy number of files that's always going to be queried efficiently. Dynamic partitioning is a second capability of our adaptive optimizer that really takes all of the manual work out of choosing an efficient partition strategy. Data lake tables, in order to run efficiently, often need an efficiently chosen partition column. Right? Partitioning, it's kind of like indexing for data lakes, right? So instead of having to query the entire table, you can query a subset of data based on what columns you're partitioning by. But historically, choosing the right partition column is guesswork and may involve a lot of trial and error. Customers often will choose a partition column that's too dense or too sparse, right? And over partitioning a table creates a lot of overhead on file ingestion and maintenance operations. Under partitioning a table creates partitions that are too large. So choosing this right is a challenge. But unfortunately, most partition strategies are rigid. You pick a column or set of columns, and that's what you get, right? With dynamic partitioning in the Qlik Open Lakehouse, you're able to choose a set of basically search columns. Think of these as the columns that you most typically are going to search by with your queries. And we will handle all of the process around deciding which of those columns make sense for rigid partitions, which of them make sense for dynamic clustering and sorting. And the end result is all you do is you feed in your search columns, and we take care of making sure that those search columns are efficiently applied to partitioning strategies. The third capability that you see here, file cleanup, right? And this addresses the snapshot and the orphan file challenges that exist within Iceberg at low latency ingestions, right? We can do continuous and aggressive snapshot cleanups to keep the size of your metadata files small and efficiently queryable. And we do aggressive and efficient orphan file cleanups so that those orphan files that are written to disk are cleaned up aggressively so they don't consume and waste storage within your data infrastructure. And the last benefit here of the adaptive optimizer goes to this auto healing and auto scaling concept, go to the idea that none of what I described so far is free, right? I mentioned it's automated and continuous, but there are compute requirements needed in order to compact data, partition data, clean up files. The compute processes within the Open Lakehouse run continuously and efficiently based on scaling requirements and configurations that you apply when you set up the Open Lakehouse. And you can control the size of your compute machines, how aggressively they scale up, how aggressively they scale down. If a machine fails or terminates, it gets spun up automatically with minimal impact on data processing. So it's very much a set it and forget it approach to compute, allowing it to scale up to handle increases in data volume, but also scale down to conserve costs. All right, we'll talk a bit more about the architecture here as we move forward. All right. But so that's the adaptive optimizer. And honestly, we spent about 5 minutes there explaining the capabilities, but I can't overemphasize enough that the objective for an end user is that when you ingest data into Iceberg at low latency, optimization becomes just a background service that's something you don't even have to think about. Everything that we described here happens automatically and continuously with minimal user intervention. Okay. Just to showcase some of the benefits and reasons why this adaptive optimizer is so important, we performed a benchmark. This is a fairly small scale benchmark. You'll notice this benchmark only operated over about 20 gigabytes worth of data, which I would argue is a fairly small amount for most data use cases. But that 20 gigs of data was ingested over 48 hours. Right? We're doing real-time ingestion. Technically, this came from an Oracle source, so we are replicating redo logs into Iceberg over 48 hours. And again, it was roughly 20 gigs of data, but ingested every minute. If you jump down to the bottom example of the benchmark, without optimizing the data, the resulting Iceberg table had 11,000 files that made up its data, right? Effectively, it was a few files every minute added to that iceberg table. We ended up with 11,000 small files. And the overhead incurred by the query engines to simply open and close those 11,000 small files was 4 minutes of query processing time, right? Now, many engines can parallelize this work, so it doesn't necessarily mean a 4-minute query, but there was effectively 4 minutes of CPU time required before reading any data just to simply open 11,000 files when querying this table, right? And that would continue to grow over time as more and more data was written to this table. Now, when we applied the adaptive optimizer to this same table during ingestion continuously, the table was somewhere between the 40 and 60 file range, right? Never more than 60 files versus unoptimized, it was over 11,000, right? And by keeping the file volume consistent and by continuously compacting data as it was ingested, the scan performance overhead of opening those files never exceeded 7 seconds, right? So 4 minutes versus 7 seconds, obviously a dramatic reduction in query overhead because of the continuous optimization that we were able to place on the iceberg tables during ingestion. And again, I can't emphasize enough, that's on 20 gigs worth of data, which is not a lot, right? Qlik has customers ingesting hundreds of terabytes of data a month. So this is a very small volume, but again, it's not volume that so much impacts the efficiency of Iceberg. It's frequency of writes, and real-time workloads are going to suffer due to many of the issues that we referenced in the presentation. The last capability I wanted to emphasize in the Open Lakehouse is this data warehouse mirroring concept, right? So ingesting into Iceberg is one thing, but then you need to be able to consume that data from wherever your data consumption layer is. And so in order to consume data from the Qlik Open Lakehouse without having to copy it again, we've introduced this concept of a data warehouse mirror. I'll use Snowflake as the example here. Data warehouse mirroring creates objects in Snowflake that point back to your Iceberg Lakehouse so that those objects present in Snowflake as any other table. You can query them as any other table, but those queries are run against the Iceberg data that's sitting in the Open Lakehouse, right? So it's a nice way you get all the benefits of the Open Lakehouse, of near real-time Iceberg ingestion at peak efficiency, but you can still leverage and consume that data within your data warehouse through the use of mirrors without having to copy that data again out to the target. So I'll take the rest of my time here today, just kind of walk you through a demo of what this looks like in the Qlik Open Lakehouse, and then we can take any questions that might exist from the audience. So let me get out of the slides here. And I will navigate directly to my Qlik Talend cloud interface. Remember, Open Lakehouse is not a separate product. It's a capability of the Qlik Talend cloud. So I'll log here into Qlik Talend cloud. And I'll first talk a little bit about architecture, right? It was kind of mentioned at a high level on some of the slides. But when you're leveraging Qlik Open Lakehouse to build out your data pipelines, the compute processes are what's referred to as a Lakehouse cluster, right? These are clusters that are deployed into your cloud infrastructure. So from a data privacy and security perspective, this will give you basically the ability to ensure that data processing never has to leave your network or your security controls, right? Qlik itself is not a data processor. The data is processed within your cloud infrastructure by these Lakehouse clusters. When you create a Lakehouse cluster, it's simply a process of defining a network integration that gives us effectively rights and permissions to create cluster resources. And then you define a cluster size. These are effectively the size of the machine that's going to provide compute processing, and you can choose any number of machine sizes based on your requirements. And then you configure scaling properties. So for example, how far down do you want your cluster to scale down to? And how far up do you want it to scale up to, right? Scaling up will increase data throughput. scaling down will conserve cost. And we will handle all of the automated scaling required to scale up to respond to kind of bursts or increases in data volume. That's fairly common, right? Maybe you have a workload that you get a lot more data ingested during business hours than you do at night. So you want your clusters to scale up during the day to handle that increase in data volume. But then you also want your clusters to scale down at night when that compute is not needed. So you can control your min max here, and then you can also control the aggressiveness of scaling. You can effectively choose whether you want to prioritize cost. So let's scale up less aggressively, right? You might incur some data freshness limitations as the scaling occurs, but you're basically saying I'm prioritizing cost over data freshness. Or you can choose the opposite. I want to prioritize data freshness over cost, right? Let's scale up a little bit more aggressively, make sure that we can handle all of the data that comes through, even if it costs a little bit more. Or you can go to the most aggressive approach. We call this consistent low latency. That's going to scale up extremely aggressively, again, based on increases in data volume. We also do have manual scaling options if you want full control over how and when the cluster scales. But again, all this is automated. You set up your cluster, you define its scaling, you define its machine size, and then all the work of managing that cluster is automated by the Qlik Open Lakehouse. So once you do have your cluster set up, the interface within Qlik Talend Cloud is then one where you build out a data pipeline project, right? And so, for example, let me go ahead and I'll set up a very quick project here. We'll call this my, I'll call this my Meetup CDC ingestion to Iceberg. I will create this within my Open Lakehouse space within Qlik Talend Cloud. And we're going to perform a data pipeline project specifically on the Open Lakehouse data platform, right? Qlik Talend Cloud supports a variety of data platforms. If you wanted to ingest and transform data within Snowflake or Databricks or Azure Fabric. In our case, though, we're going to choose the Open Lakehouse data platform. And I will then choose connections to the different resources needed in order to ingest into my Open Lakehouse. And specifically, there's two resources. One would be an Iceberg catalog, right? Iceberg, there's a variety of catalog options for Iceberg. In this example, I'm going to choose an AWS Glue catalog. I've already created the connection to it. It's a pretty simple configuration. You just need the AWS account ID and the catalog region that you want to leverage the Glue catalog within. We then have a resource here, which is a landing connection. The process of real-time ingestion into Iceberg is technically a two-step process. We collect raw data from the source into a landing target. It's effectively raw data stored on S3. We then process that raw data into Iceberg. So we can set up now an S3 bucket that's going to act as our landing target for raw data. And then we choose our Lakehouse cluster. Right? Again, these are the compute processes that we want to leverage in order to drive this particular ingestion pipeline. So we now kind of have the shell of our project set up. Our project is going to ingest into Iceberg using the catalog connection and S3 bucket that we've defined and using the cluster resources that we've pointed it to. From here, the process is now onboarding data from our source. Right, and we support, again, all the sources that Qlik Talend Cloud provides, CDC sources from platforms like Oracle, SQL Server, Postgres, even support platforms like DB2, SAP, SaaS connectors like Salesforce. Again, pretty wide range of connections here. In this example, though, I will choose a Postgres SQL source that I'm going to ingest data from. And specifically, I can choose the tables that I want to ingest data from my Postgres source. I could simply select all of them if I want to ingest from every table. In this example, though, I'll choose two tables from my source that I want to ingest into Iceberg. Right? So we add those tables as data sets that I want to include in this ingestion. In addition to an inclusion, we can also do an exclusion, ingest from everything but these few tables. Makes it very easy to select data from a very wide range of tables on the source. Right? A couple of different methods that we can choose for ingestion. CDC is our most common method. That's a real-time continuous ingestion process, in this case using the Postgres write-ahead logs. We do also support a reload and capture for those that might want more of a batch-oriented ingestion. And here you'll see we have the option of preserving type 2 characteristics within your source systems. Type 2 referring to slowly changing dimensions around each row that gets ingested. If you just want the current state of the row, we can onboard data only. If you want to maintain a full history of changes within your open lakehouse, you can preserve those type 2 characteristics and maintain full row-based histories within a queryable Iceberg table. So I've set up my project here. I've chosen my source. We then have a landing target. This is going to effectively take data from the source and ingest raw data into that S3 bucket that we're using for landing. There's a preparation step in Qlik Talend Cloud that sets up the landing zone for ingestion. Once the task is prepared, I can then execute it, and it runs continuously, right? Reading log records from the source, writing them into landing. Technically, this landing process starts with a full load. That's effectively a starting point, takes a full copy of the source table and applies it to the target. And then once the full load is complete, changes then stream into the landing area. Right? Once we've prepared and set up landing, we can then prepare and set up our Iceberg storage task. Right? So this tile here is what kind of represents the Iceberg-based functionality within the Open Lakehouse. So as an example, we can effectively see each table that we're going to be ingesting data into. We can, if we need to, apply some transformation logic right within this task. If we need to change a data type or do some string parsing, sometimes customers like uppercase or lowercase table names or column names, right? All those are available as transformation rules. Let's say in this use case, though, I just want to ingest the data as raw. So what I'll do is I'll go into my project settings here. I'm just going to set a prefix just to make sure I don't ingest the same table name twice. And then we can go ahead and, much like I did with the landing task, I can prepare the storage task for Iceberg ingestion. Once the preparation step is complete, I can then go ahead and run it, and it will effectively start loading that data into Iceberg tables. Right. So honestly, what I wanted to emphasize here with the demo is really just this simplicity in doing a real-time, continuous CDC-based ingestion into Iceberg, right? So really just a few steps in a wizard now has us running a continuous streaming data pipeline into Iceberg tables on the target side, right? Now this is going to take a few minutes to do the full load and kind of set everything up. So I'll now switch just to a project that I've had running for a few days now, just so you can see kind of what it looks like once it's been running in production. And here I've got the same project that I just showed you. It's just been running for a while, right? So we have our landing task, we have our storage task. If I look at the monitoring within our storage task, you'll see that we've ingested roughly almost 37,000 changes into this target table since the project was created. And you'll see there's a concept over here referred to as unoptimized changes, right? This reflects that adaptive optimization that's happening in the background. So right, we've processed 36,000 changes. All 36,000 changes are queryable in the target. 10 of those changes are awaiting the adaptive optimizer, right? So ideally, you'll always see a small number of changes in the unoptimized section. That gives you some indication that we do have some future work to do, but we're keeping that number small so that they're efficiently queried on the target system, all right? But you can track this as you need as we ingest and as we continuously process data into the Iceberg tables that we're writing data into, right? Now, ingesting data into Iceberg is one thing. We then need to also make this data accessible and queryable by whatever our consumption engine might be, right? So if you're using engines like Athena or Trino or Amazon EMR or something like that, you can now just go ahead and query these Iceberg tables as you would any other Iceberg table within those platforms. But let's say you're a Snowflake user, right? And you like the idea of Iceberg-based ingestion of your raw data so that you can have very high throughput, very high efficiency, and very low cost ingestion into Iceberg, but you still want to make that data accessible within Snowflake, right? So that's where mirroring comes in. We can create this mirror task. The mirror task allows us to create objects in Snowflake I'll give you an idea of what we're actually creating in Snowflake we've got an iceberg table. So this is what Snowflake refers to as an external iceberg table that Qlik is creating in Snowflake that points to your open lakehouse table within the catalog that you chose. And then we're also creating views on top of that data to give you different representations of your source system, right? You've got kind of a standard view, which gives you the point in time live view of the table. And then because we decided to maintain type 2 characteristics within our target, we also get a view that gives you full row-based history of every update within the source system. All right, so you can see for each primary key column, when was it inserted, how many times was it updated, when was it deleted. The history table will give you that full history. The standard table will give you what is the current representation of the source. But you have the option of having both tables persist within Snowflake. But again, this is a nice option. Again, it's not copying the data to Snowflake. It's simply creating objects in Snowflake that allow you to reference your open lakehouse tables and query them as any other Snowflake table, right? So if I go into my Snowflake installation here, I can go ahead and run this query. This is a query that's running against that Snowflake mirror that I showed you. It's again going to look and function like any other Snowflake table. But again, the data is coming from the iceberg tables that Qlik is ingesting into and optimizing, right? And just as kind of a final example of the demo, this isn't necessarily no longer open lakehouse related, but let's say we now want to leverage the rest of Qlik Talend Cloud to transform and process this raw data. We can do things like, for example, we may want to mask PII within a set of tables. We may want to do some normalization of data, right? If you look at my country column here, you can see I've got different representations of the United States, just a kind of poor quality source data that I might now want to clean up. Within Qlik Talend Cloud, we can feed these Snowflake mirrors into transformation tasks. Those transformation tasks can do everything from hashing sensitive columns to maybe filtering out bad data, maybe normalizing string values, right? Convert all USAs into USs. And then within Qlik Talend Cloud, we're now performing additional transformations. That transformed data can be written back into Iceberg tables on Snowflake or into Snowflake native tables based on where you'd like them to be written to. But this gives you the ability to do full end-to-end transformations in near real time, leveraging Iceberg as that kind of bronze raw layer of data that's being ingested. And here you see your hashed email addresses, you see your normalized country codes, and we can do lots of other transformation types, aggregations, joins, filters, enrichments, based on what your requirements for transformations might be. So that's effectively where I wanted to stop the demo. I think at this point, I did want to introduce a little bit of roadmap. So the Qlik Open Lakehouse is now GA, right? We actually announced the Qlik Open Lakehouse at our Qlik Connect conference in May. We ran an early access program over the course of the summer to get the product into partners and customers' hands pre-release. And then it was actually a few weeks ago in the middle of September, the capability is now GA. So any user of Qlik Talend Cloud, whether you're a production user or an evaluation user, now has the Open Lakehouse functionality available for use. I mentioned the 3 core capabilities that are now available: direct Iceberg ingestion at scale, adaptive optimization, and data warehouse mirroring. We do have a rich roadmap that we're looking at releasing over the course of the next few quarters. The first I've already alluded to, that's ingestion from streaming sources, most specifically Kafka and Kinesis. So anyone using Kafka or Kinesis for real-time messaging will be able to ingest that data directly into Iceberg tables. Right now, the Open Lakehouse runs exclusively on AWS. So for those of you that are AWS customers, you can take advantage today. For those of you that are not AWS customers, we have plans to increase our cloud support, first coming with Azure, and then eventually coming with GCP down the roads. But Azure support should be coming at some point over the next few quarters. I mentioned our data warehouse mirroring. Data warehouse mirroring is currently targeted at Snowflake with support for Databricks and other warehouse platforms like Redshift coming soon. There's this idea of streaming transformations, right? Qlik Talend Cloud currently supports more batch-oriented transformations, but we have many customers who are interested in leveraging streaming transformations so that in near real time, you can bring data event by event, row by row through a transformation architecture, and that will be coming as well. And then also lots of capabilities around ensuring high quality data coming within a set of functions into the Open Lakehouse over the course of the next few quarters. So thank you all for kind of sitting with me through the Open Lakehouse introduction and demo. I think at this point we can turn it back over and close out the meeting and take any questions that there might have.